In example 2 here, we're going to continue to look at the same cardioid, 1 plus sine theta. We're going to look at it as theta ranges on the interval from 0 to 2 pi, and we're going to be curious about where there might be horizontal tangent lines, vertical tangent lines, and this new thing that we're going to refer to as a singular point. For the moment, don't worry about the singular points. I'll define those a little bit later into the video. If I was to take a look back at the actual graph that I see here, I'll see that there are pretty obviously some spots where I might expect some vertical and horizontal tangent lines. I might expect that maybe somewhere up here at the top I could draw a tangent line that's perfectly horizontal. Maybe somewhere over here at the sides I could draw some verticals. And so I should be able to try to find these. Now if I go back and I take a look at my function here, I'll notice that since it's the same as what we used in the last video, I can go ahead and actually just take all the information that we calculated in the last problem and import it here. So I'll say we know that dy dx is equal to, and I'm just going to go back and grab this from what I had in the previous question. Again, it's the same function. So it's cosine sine, and so I'm going to go ahead and start to write this down. It's the cosine of theta times the sine of theta, and then plus a 1 plus sine theta cosine theta, and then I had a cosine squared of theta minus the 1 plus sine theta cosine theta. Oops, sorry, sine theta that down there. So if I have all of this here, and this is equal to my derivative, it can start to become pretty easy to see when exactly I might be able to get horizontal and vertical tangent lines. In fact, to help with this, I'm going to go ahead and I'm just going to kind of divide up my page right now into kind of two different halves. So let me see, I'm going to go pretty much all the way down the page. And the purpose of this is going to be to try to split apart what's going to be happening when I get horizontal and vertical tangent lines. I'll tackle one of these on either side of the line. So when I take a look here at a horizontal tangent line, I know it's a tangent line with a slope of 0, and that would mean that my numerator up here would have to equate to 0. So over here, I'll state to get a horizontal tangent, we must have that numerator, that cosine of theta, sine of theta, plus the quantity 1 plus sine theta, which is multiplied to the cosine of theta. I would need that to be equal to 0. I would also need the denominator to not equal 0 at that point. I can't get a horizontal tangent line if this comes out undefined. So this is what I would need. I need to find all the values of theta that can make this work. Notice on the other side, I can say that to get a vertical tangent, we must have, and I would need my denominator, which is that cosine squared theta, minus that quantity of 1 plus sine theta times the other sine theta. I would need this to equal 0. So I'm going to actually have to go through and do everybody's favorite topic, which is solving trig equations. Okay, it's probably been a while since you've solved some complicated looking trig equations, but I'll help to try to guide you through it here with this example. And in example 3 in these notes, I'll leave that for you as one to try to go practice with on your own. Well, let's take a look over here at what I have at the start. On this left side, if I'm trying to find horizontal tangents, the best thing that I can try to do typically is oftentimes to try to factor some things. Because if I have something equal to 0, and I can change the other side into one item times another, then it's really easy to figure out what the values of theta are that might make that true. So notice here, what I can see is in common immediately between the two terms is that there's a cosine in common. So what would happen if I was to take that cosine of theta and just actually pull it out? Notice what I'd be left with is a sine of theta and then a 1 plus a sine theta. This is what I would be left with. Now this is again immediately amazing because now I know that I have one thing times another equals 0, which means one of those two pieces has to be 0. If I simplify this down a bit more, I'll see that this is actually even better than I could have hoped for, because I'll notice that each of the pieces, that is the cosine and this set of brackets, that might be equal to 0 here, only contain a single trig function, which means they're going to be unbelievably easy to solve. So I'm going to go ahead and start to take a look here at these two different ideas that I need to explore. When will the cosine of theta be equal to 0? And I won't say and, but let's say or. When will it be the case that 1 plus 2 times the sine of theta will be equal to 0? Well, the cosine of theta equals 0 is pretty easy to spot. Remember that that's going to happen at all of the points coterminal with pi over 2 and 3 pi over 2. So from this piece, I'm going to easily get that my theta should be something like pi over 2 and 3 pi over 2. Again, in the question, I'm only dealing with angles that are inside the range of 0 to 2 pi, so I don't have to worry about any other angles. Notice over here, this is going to get me sine of theta is equal to negative 1/2. And if I think about when that happens, if the sine's going to be negative, I got to be in one of the lower quadrants, somewhere over here and here. And this should then end up being my angles of 7 pi over 6 and 11 pi over 6. So these are all the different values that I can plug in for theta on the interval 0 to 2 pi that give me my numerator equal to 0. Okay, well let's do the same thing now for the other side before we start to declare where we're going to end up with horizontal and vertical tangents. Now this side over here, I'll notice right away that I don't have anything in common that I can immediately factor out. So I'll just go ahead and start by maybe doing some distributing. I'm going to distribute in this sine theta and this negative at the same time. So let's see, I have this negative sine theta, and then I'm going to have a negative sine squared theta. And all of this is equal to 0. Again, this is really messy to now try to work with. I'd like to try to go ahead and either attempt to factor something or convert all of this to a single trig function. Notice like on the other side, when I had an equation with a single trig function, like we were able to get down here to near the end, it was way easier to go ahead and solve for theta. And so what I'd like to try to do at this point is to see, are there any identities that I might know that could help me transform this into something with only a single trig function, or a single kind of trig function, like all sine thetas? Well, actually, that's definitely possible because I could go ahead and I could update this cosine squared. I'm going to go ahead and replace that cosine squared with a 1 minus a sine squared theta. So notice everything else here is going to stay exactly the same. But again, the advantage of doing this is that now I have all one kind of trig function. They're all sine thetas, just to different powers. If I was to rewrite this, you'll notice here that I have a negative 2 sine squared of theta. I have a minus sine theta, and I ultimately have a plus 1, and then my equals 0. And so what this actually looks like is something like a quadratic. This is almost kind of like a negative 2u squared minus u plus 1 equals 0, right? I have a shape that's kind of like this, where u is kind of playing the role of a sine. And the reason that we really like that is because now I could go ahead and just imagine, well, if this was a quadratic, I would try quadratic formula, or maybe I would try to factor to solve something like this. In this case, I'm going to try to factor to at least see if it's possible to avoid the use of the quadratic formula. So I'll start by saying, well, maybe I would need to have something like this, a negative 2 sine theta and another sine theta. That would at least, when I distribute, allow me to end up with my negative 2 sine squared. But now I need something over here to create positive 1. And I want this middle term here to be negative. So I'm going to try a minus 1 and a minus 1. Let's just quickly double check. If I multiply everything through, let's see, I'm going to get positive 2, and then I'm going to get negative 1. Ooh, that doesn't quite work. I think the middle term's off here. I could try something like 2 positive 1s. That would create what I need. Same with this. Then I get negative 2 sign and a positive sign. This will work perfectly. Again, since I have two things now that are multiplied together to equal 0, it's easy to deal with each of these separately. So I have negative 2 sine theta plus 1 is equal to 0, or sine theta plus 1 is equal to 0. So let's see. The first one here is going to tell me that my sine of theta is going to need to equal a positive 1/2, and I know that that's going to happen at some points around here on the unit circle. Specifically, that's going to be at pi over 6 and 5 pi over 6. On the other side, I'm going to get my sine of theta needs to be equal to negative 1. I know that that only happens down here, and so there's only one value of theta that's going to make this work on the specified interval. Okay, so I've solved both of these now for when I can get horizontal and vertical tangents, and I'm going to notice something. I'll notice again that if the numerator and the denominator turn into 0, I'm screwed. I can't get vertical or horizontal. So I want to quickly identify, are there any thetas that will make this numerator 0 and also the denominator 0? And yes, it looks like there is one. This 3 pi over 2 value is going to make the top and the bottom 0. And it's at this point where we're going to have what we called a singular point, which is what we didn't define in the beginning, but said we would talk about later. Before we go through and finish this up, or completely finish this up, let me go ahead here and redivide the page. And then I'll go ahead and summarize what we have down below. So on this question, I wanted to find where all of my horizontal tangents were located, but specifically what points they were located at. What I have right now is that my horizontal tangents are going to be occurring at 3 different points. And so I'll set up these 3 points. And I know the different angle measures. I have an angle measure of pi over 2, 7 pi over 6, and 11 pi over 6. But what I don't know is the value of r. But of course, since I have an equation that relates thetas to r's, I can easily go back and find what I'm going to end up with for my r value. Notice at pi over 2, my r value is going to become 2. At 7 pi over 6 and at 11 pi over 6, I'm actually going to end up with the value of 1/2, because I believe the sign creates negative a half there, and 1 plus negative a half is a half. So horizontal tangents are going to occur at these points. When I talk about vertical tangents, I can do the same thing. Vertical tangents are going to occur really here just at 2 points, one with the angle pi over 6, and the other with the angle of 5 pi over 6. I know that if I plug both those into the sign, I create a 1/2, and so each of these is going to have a 3 over 2, or a 1.5. And when I take a look then at my final idea, which was my singular points, I know that my singular points happen at any time when my derivative creates a 0 over a 0. And that apparently here happened at 3 pi over 2. And if I look at what r value I get when I plug in 3 pi over 2, I'm going to get negative 1 plus 1. So that's going to be an r value of 0. Now, I should be able to go back and test this out based on the given picture. I should be able to make sure that everything that I see in the picture aligns with these points. Let's take a look first at these horizontal tangents. I'm going to start by looking at the point, rotating towards pi over 2, and then walking 2 steps. Well, if I look at this, if I rotate towards pi over 2, and I take 2 steps out, I'm going to land right up here at the top. And if I look at this, you can ignore that. If I look at this, I'm going to see that there is going to be a horizontal tangent line there, like we predicted. I can also look at 7 pi over 6 and 11 pi over 6 and stepping out a half. Well, let's see. 7 pi over 6 would be facing out in like this direction, right? Just a little bit below that horizontal x-axis. And if I took a half step out and hit the curve, I might land right here. And yeah, I could imagine like a horizontal tangent there. 11 pi over 6 would be facing over here. My vertical tangents are going to be corresponding to those points of staring in the direction of pi over 6 and walking out a step to hit this edge. And you'll notice that my singular point happens staring downward at 3 pi over 2 and taking 0 steps. At this kind of cusp point that I have here is where that singular point occurs. So obviously there's a lot to answering a question like this, and it does take some time and some practice to get used to. I'm going to leave example number 3 as one for you to try on your own, and of course you can check the solutions up online in Blackboard.